Let's start with chapter 1, introduction to the microprocessor and also microcontroller. So if we look at this, now we have two, microprocessor and microcontroller. What are the different? What is microcontroller and what is microprocessor? So we will see in this chapter what are the differences between the two. All right. So what we will learn in this chapter is first is the overview of a processor. What is processor actually, right? And we will look at what is called the one of the processor in processor architecture. We can say that, call it RISC or reduced instruction set computer, and CISC or complex instruction set computer. What are the differences between the two, and why is this important? And next, we will look at the microprocessor system. All right. So we have the microprocessor and we have the microprocessor system. What are they? Yeah. And yeah, the last one, we will look at what is microprocessor and what is microcontroller. What are the differences? Right. Now, um, what what is microprocessor? What um, so this is the definition from uh, books. Yeah, a microprocessor, or in short, we call it, this is micro P. All right, microprocessor is a programmable digital electronic component that incorporates the function of central processing unit or CPU on a single semiconducting integrated circuit. So this is the definition. This means that uh, the digital electronic component, you have learned how to design a digital circuit, right? In digital electronic, in digital design, right? So that is digital electronic circuit, and this is programmable, means that you can program it. We will see what is mean by program, and it will do the function of CPU or central processing unit, means that it can process or manipulate data, right? So let's in digital design, we have learned how to design the ALU, right? How to design a small or custom processor in chapter 6, right? So the circuit that we have, for example, adder, multiplier, that can do arithmetic and logic function, is the processing unit. All right. So the electronic circuit that do the processing work on a single semiconducting, means that on a single chip, single IC, is a microprocessor. All right. The IC that do the or perform the processing or data manipulation or calculation, computing, all right, is a microprocessor. The term micro means that it is small, all right? So when the microprocessor was invented, long time ago, we will see how long, all right? It is in micro in size, micrometer. But nowadays, yeah, it is in nano, but the name is still microprocessor, not nano processor, right? Because the name is uh, is is remain it's a well-known name, just like uh, the transistor that we have today. Yeah, the transistor that we built microprocessor. we call it MOS, right? Metal oxide semiconductor, MOS. But this is from the first version of the transistor. Nowadays, this is not metal anymore, right? The conducting part is a more on the semiconducting part already, but the name is still metal, right? MOS, metal, same as this one. This is a small in silicon, on the silicon, right? On the chip IC, that can perform computation. That is microprocessor. All right, and we have a lot now. The famous one is, of course, Intel in your PC, in your laptop, all right, or AMD, which actually same architecture as Intel, right, with only some differences, yeah, the detail differences, but by in terms of architecture, it is the same architecture. We call it based on x86 architecture, right? We have the ARM, which is the most uh, popular processor in the world, because it is almost inside every handphone, mobile phone that we have today, right? It is from or using the ARM architecture. And in our course, this course microprocessor, we will learn the ARM architecture. This is the technology that we will use in this course. All right. So in your handphone, yeah, in your phone, it is the ARM microprocessor. We have from Altera. Altera is actually part of Intel now. We have NVIDIA, the GPU. We have the MIPS, we have admin, we have microchip, and we have many more actually, many more, a lot, yeah. So that is the mm, the meaning of microprocessor. What is microprocessor? So microprocessor is this code I get from Intel, all right. Said that the microprocessor is one of the unsung heroes in the modern era. What is unsung heroes? Unsung heroes means that the hero that is not uh, we cannot see, right? Uh, work in background, right? Same like microprocessor in our PC. We cannot see the microprocessor, right? We can see our PC, all right? So if you buy a PC, right? You buy a laptop. So there are a lot of laptop brand that we have. We have Lenovo, we have Acer, we have Dell, all right? There are a lot of brand, but inside using the Intel microprocessor or AMD microprocessor, right? So it is inside. So that is why Intel said it is one of the unsung heroes. Like the car designer was vehicle give the racing driver glory, right? Same. This is just example, right? The microprocessor make quite incredible things possible all over the world. Each year, we benefit from faster and more efficient performance, which improve not just computing, but also numerous fields from retail and industry to agriculture and vehicle safety. So every industry nowadays, or everything that we look, yeah, electronic devices that we have today, there is microprocessor inside. This year, the humble microprocessor celebrates its 51st birthday. So actually, the microprocessor was invented 51 years ago. The processor is long ago actually, because before that, the processor is not in the form of microprocessor. Remember, microprocessor is the processor inside the IC, inside the chip. But before that, the processor is big, yeah. The size is maybe one room, yeah, because it is built from the switches, microprocessor, transistor. Okay, so if you use the transistor, the big transistor, just imagine if you have 1,000 transistor, what is the size of your microprocessor already? Okay, that's why we use the IC, the semiconductor, to build the microprocessor, because we can make it small, right? But before 1970s, the processor is big, because the technology that we built the microprocessor is, we don't have the, or we're not able to build it on the semiconductor yet, right? But Intel, yeah, the first who built the microprocessor, uh, able to create the microprocessor on the semiconductor, right? So 51 years already since 1971, yeah, older than me, and of course older than you, right? Actually, it is not that long time ago, right? 51 year is quite young, quite new. But if we look at the, I will show you later, if we look at the evolution of the microprocessor, we can say that it is very amazing, right? That the technology can can evolve, can improve very fast. Yeah, from the first version of the microprocessor to the processor that we have today. All right, it has become the brain of literally billions of devices. Yes, any devices that we have today got microprocessor inside. Without the microprocessor, they would not have existed. Just imagine if we don't have microprocessor, everything, every technology that we have today, we we will not have it, not even existed, right? Even your everything. What to say? Of course, your mobile phone, your PC, your mouse, even your keyboard, right? Your TV, everything nowadays, right? We are in dark ages, right? If we don't have microprocessor, so that is why it is important. That's why you need to learn this, right? Electronic engineering student need to learn microprocessor. If you say that you are electronic engineering student and you don't know microprocessor, you don't learn microprocessor, you are not electronic engineer. Okay, so that is why it is important, right? So this is the evolution. But before this, I want to show you, yeah, if you can, go to internet and try to search for um, microprocessor, like this transistor count. It will list almost all the processor that we have, right? Starting from, if we look at the first microprocessor, is actually Intel 4004 is the first. Yeah, this MP944 is not the microprocessor. Actually, it's a processor that is not inside one chip. It is many chip. It's built from 28 chips. All right, although it is earlier than uh, than um, than Intel, right? In 1970. Okay, so uh, this is actually we cannot call this first microprocessor. The first microprocessor is the Intel 4004, and the size is 4-bit, right? 4-bit. Remember how to design the adder or the ALU 4-bit in your digital design? This is small, right? Your assignment is even more in size, 8-bit, right? But of course, microprocessor is more complicated because you need to have the control circuit, and those control circuit is It's just like you build the controller in the design, but it's more complicated. But that is how we design the microprocessor, right? And there are a lot since then. And this is the number of transistor in the microprocessor. The first one is about 2,250 transistor only, right? And the size is, you see the size is 10,000 nanometer. So it's about 10 micrometer, right? So quite big. This is in micrometer size, micrometer in size. And let's look at today. So if you browse more, go down, there are a lot, see, a lot until we have uh, till maybe look at the Intel first. This is GPU already, Intel. Where is Intel? Okay, we can see the AMD Ryzen 9. This is quite new processor here. And you can see that the size is 7 and 12 nanometer. And you can see Apple M1 Ultra here, 20 core. And the size is 5 nanometer, which is very small. This is Intel. Intel to 2022 is 10 nanometer, right? But Apple one is actually based on the ARM microprocessor. And yeah, remember we learned the ARM architecture in our class. All right, ARM is not selling the microprocessor. Yeah, ARM, we will see later. ARM is the company to design the microprocessor, and it sell the design to many of the microprocessor manufacturer. For example, one of them is Intel, not Intel, sorry, Apple M1 or Apple A15. That is the microprocessor inside the MacBook, right? It's based on ARM architecture, right? Or the Samsung phone that you have today, or any phone that you use the Qualcomm Snapdragon, right? Use the ARM architecture as well. All right. So most of the mobile phone that we have today is based on ARM architecture. So we will see later. Yeah, but just to let you know that, you see, from previously, you have the size of the transistor is 10,000 nanometer or 10 micrometer in 1971. And today, 51 years later, we have 5 nanometer, right? How many times this is smaller? And this is, if you look at the what we call the Moore's law, right, says that the size of the microprocessor, the size of this transistor will reduce by factor of 2 or exponentially in every 2 years, right? So that is why we get very small now. And see, in the next 5 to 10 years, you will not see any transistor that is smaller than this. Very difficult to see, because this is actually bottleneck already in terms of technology. All right. So just for your knowledge, yeah, because the size is used to control the flow of electron or flow of current. So 5 nanometer is very small, and if you go beyond that, yeah, so the quantum mechanic effect of how the electron behave will be different. So the transistor that we have is actually used to control how the current flow, whether we block the current or we off the transistor. or we let the current flow, or we on the transistor, right? So we can control if the size of our transistor is more than 5 nanometer. But if less than 5 nanometer, it is very difficult to control the flow of the electron. Some of the electron may escape from the what we call the channel, right? If you learn electronic, so we call it tunneling effect. All right. So this is the bottleneck already. If you read the technology trend or journals, right? So it's quite challenging after this. What is the technology that will replace uh, maybe the transistor? So one of them, we call it quantum computer and so on. But for now, we still use the transistor as the switch implementation, or to implement digital value in microprocessor, right? So, and the number of transistor, remember the previous one, Intel, 2000 plus transistor, and now you have, uh, what is this number? 114 billion transistor, right? Billion. How many times the number? See? So the size is very big in terms of transistor count, but the size, because you reduce the size, you see the relation. Because you reduce the size of the individual transistor, that is why you can fit more transistor on the single chip, on the IC. All right. If your transistor is is 10 micrometer in size, then just imagine what is the size of your microprocessor if it is 100 million billion transistor like this. It's big, very big. So you cannot do that. And if that big, the power consumption is very, very high. All right, it will burn everything. Okay, so that is why we reduce the size of the microprocessor. It will reduce the power consumption. It will increase the performance, increase the speed, and so on, right? But now we reach the bottleneck already, right? Because go beyond 5 nanometer is very difficult, right? So that is the things. Now let's go back to this. So you can read this, you can look at this later, go to the internet and search for transistor count, microprocessor transistor count, or just transistor count. So you will be here in this Wikipedia, right? So if we go back to this evolution of microprocessor, so you can see the microprocessor is inside this thing, right? You cannot see the microprocessor, but it is used as a brain for these devices. So for example, in the first microprocessor in 1971, the Intel 4004 is used in the calculator, right? And this is very popular that time. Uh, yeah, it is the name is Unicom 141P calculator was the first and very first device to feature a microprocessor, right? So the Intel is used here. And later in 1977, we can we can say that this is more computer look alike, right? This is looks like our computer today, that we have the monitor, we have the keyboard, yeah, or we can call it all-in-one home computer already. And if you look at the year, so this must use the uh, if you look back to this in 1977 here. So yeah, it should be this, the Intel 8085 microprocessor. All right. Normally the processor at that time using this 8085. It is an 8-bit microprocessor, 40 pin, right? And we have about 6,500 transistor, and the size is 3 micrometer or 3 nanometer, 3,000 nanometer. All right, getting smaller, right? and this is the microprocessor. It is Intel used here. And in 1978, we have first embedded processor, means that the processor that is not used in the computer, but it is in home appliances, for example. So, for example, washing machine, yeah, use the microprocessor inside. We call it embedded processor. And in 1980, we have the arcade mania, the arcade game. If in 90s, in 80s, yeah, this type of game is very popular, right? So the first laptop in 1981, you see, this is the first laptop. We can call it first laptop, and look at the weight. This is not portable at all, right? And the size of the screen is 5 inch. Okay, so grandfather of modern laptop, we can say so. And we have the game console in 1986. Looks like this, yeah, the first console. Now we have PS, right? So the first invention is looks like this. And we have in 90s, yeah, the personal computer was very popular at that time. So for example, my first computer was in 1993. So let's look at the processor that we have at that time. 93, not even Pentium yet. My computer is yeah, this one. But this processor was invented, yeah, or produced in 1989, but my computer is in 1993 already. But the processor is Intel 84X 486. So this is actually the architecture that is still used in the iCore 7, iCore 9 today, right? But the difference is we have more transistor, we have more features, the size of the cache is bigger, the memory is bigger, and so on. All right, but the architecture is actually the 86 architecture. We call it 86 architecture. So if you look at Intel and go to Window and then go look at your um, computers, you can see that it is based on x86 architecture. Means that it is based on x86 architecture, right? So my first computer was in 1993, and yeah, see the size is 32-bit in size, quite big actually. Yeah, and the price is before I tell you the price, I want you to guess uh, the price. I give you the specification. The specification of my computer at that time is this, running at 33 megahertz. The RAM size is 4 megabyte. 4 megabyte. Yeah? Today computer at least you have 4 gigabyte, right? 1,000 times 4 or 8 gigabyte already. But my computer, my first computer was 4 megabyte RAM. The hard disk is 100 megabyte. Today the hard disk is at least 500, 512 gigabyte, right? SSD. Last time the hard disk is yeah, the disk, the hard disk, the mechanical disk. Running Windows 3.1. We call it Windows 3.1, the original window at that time. And yeah, can run Word, Microsoft Word, can run Power. At that time, I don't think we have PowerPoint. but Word got, uh, and some games, yeah, can play games. 3D games at that time is different from with the computer that we have today. Now, do you know what is uh, the cost, the price of this computer at that time? And I can say that that was quite high spec at that time. Can anyone can guess what is the price of the computer? 10K. Wow, Abdul Hakim, that is too low. 3K, too low. This is not high spec. My one is high spec. Yeah, around that. A little bit less than 6K. 5K plus. No lah, just yeah, I can afford to. Not me, but my father. Yeah, 5K plus at that time, right? But yes, no, not at that time. Not everyone has computer PC. Yeah, you are lucky if you get that. But I just want to share with you that about 20 years plus, right? The technology is um, the evolution of the technology is very fast, right? So just like what we can see here, okay, from 1991, my computer looks like this, exactly like this, right? We have the CRT monitor like this, color monitor, okay. Back then, the low spec one is not even color, yeah, the monitor, right? In 1997, we have the MP3 player, right? Because before, just 3 to 4 years before 1993, MP3 format was invented, right? So the player was, yeah. Before that, we have the I don't think you know that, we call it Walkman, yeah, by Sony. You know that? Let's look at in the internet. This is the new one, the old what 1990 something like that. Yeah, looks like this, right? Looks like this, and use the magnetic tape, right? Uh, the memory, the type of memory that we have today, right? This is the 90s technology, but uh, in 1997, now we have the technology revolution again in terms of how we listen uh, the music, listening to music, right? Using the portable devices like this, and you can store thousands of hundred of song, right? And BlackBerry in 1999, so it's a kind of um, the smartphone, the first smartphone, yeah. And we have iPod from Apple. So before this, Apple is uh, more on computer, yeah, computer. Uh, and after that, in 20s, Apple start to make the handheld devices, Yeah, start from iPod before the iPhone, right? And actually, the first tablet was invented by Microsoft. Yeah, 2002. It's running the window, and this is not famous. This is not that popular because window running on tablet is not that suitable, you know. And it's used not the it is touchscreen, but you cannot use your finger. You need to use the what you call it the stylus, right? Because the screen is not capacitive. This is the old technology. You need to use the stylus, right? And in 2008, you have the netbook. Netbook is a very small laptop, right? Because at that time, actually, we have the desktop, the notebook, right? And we have the netbook, but the netbook is not popular. If uh, is not popular, it's die out after that. All right. 2010, we have iPad by Apple, and which is very popular. And 2011, Intel introduced the Ultrabook. Ultrabook is the laptop that is uh, lightweight, thin, uh, and yet powerful, right? We call it Ultrabook. So the laptop that I have today is kind of an Ultrabook, right? So actually, it was introduced back in 2011. We have the digital signage, right? Actually, it's a TV, right? And today we have what is called the AI, or artificial intelligence, right? We have robot that, or we call it machine learning, right? The computer or robot that can learn, can make decision, right? So this is called AI, right? And it is actually drive, yeah, the core, the brain of that AI robot is actually the microprocessor. You need microprocessor to be the brain of the robot. So uh, the difference is that you need to write the program to implement the AI. And also now we have the hardware that is designed for AI, but it is still based on microprocessor architecture, right? So the microprocessor is very important. It is history, yes. It is now. It is future. It is our future, right? So again, this is why I want to stress that. I want to tell you that microprocessor is important, and this is why you need to learn microprocessor, right? That is the story. That is the evolution. Just want you to know the story behind, right? Now let's go beyond that, go into detail, go into a little bit more architecture. We will learn um, the details of the architecture later in chapter 2, but let's go a little bit deeper, right? This is just general knowledge. Yeah, you can read from the internet, and this is just general knowledge for layman uh, knowledge, right? But for us, we need to go beyond. We need to go more. Let's look at the list: RISC and CISC architecture. So there are two types of computer architecture. We can say that. Yeah, two type of microprocessor architecture in terms of what we call the instruction set architecture. So what is instruction set? We will see in detail in chapter 2, 3, and so on, right? So basically, instruction set is uh, the code that is used to instruct the microprocessor to do the task, right? So because the microprocessor is actually a hardware, a piece of hardware, just like you learn or you did in the design, this is a digital circuit comprises of ALU circuit, the control circuit, right? So in order to make it work, right? Remember last time you have uh, the RTLCS table, right? Remember that? Anyone remember RTLCS table? So in what you have learned last in digital design, you create the code, the control code, the sequence of control, right? The sequence of control code in the RTLCS table. So that code will instruct your hardware to do this, this, and this in sequence, right? First, what you need to do, you move the data from R1 to R2, or from the input to R1, for example. Next cycle, you add the data and you store the result in another register. And next you do this, and next you do that this, right? So based on the code that you give to your hardware, right? So that code is actually the instruction. So in the microprocessor, there are a lot of code that will instruct the microprocessor how to perform job or task. So the first code is like this. It will get the data, for example, from memory to the internal register. And the next code is to add the data from in the register R0 to the register R1, add together, and then save the data back to the memory, for example. So it's based on that code. So that code is called an instruction. Instruction. All right. And this instruction is actually a program. So in this course, we will learn how to write the program, how to write the instruction to instruct the microprocessor to do the job. For example, we want to the microprocessor to calculate numbers. So what is the code? What is the program to do that? Right? That is the meaning of that. So there are two types of instruction set architecture. The first one is CISC, or complex instruction set computer. Second one is the RISC, or reduced instruction set computer. So the first generation of the computer is in the form of CISC computer, or complex instruction set computer. This is the first generation of the microprocessor. Next, yeah, in about 1980s, there is another type of microprocessor was introduced to reduce the complexity, the hardware complexity of the first generation microprocessor, it, where it is called the reduced instruction set computer. Okay, so that is the story. But uh, in term of architecture, what is the difference, right? So this is the difference. These are the differences. So CISC is the original microprocessor ISA, or instruction set architecture. RISC is the redesigned ISA that emerged in the early 80s, right? Just like I said. Number two, instruction can take several clock cycles. Instruction takes less clock cycle. What does this mean? So to understand this, let's go back to what we have learned in data design. So actually in this course, if you haven't took or have not learned the data design yet, this is a little bit difficult for you to grab or to understand the idea. So that's why you need to learn data design first before you learn this uh, microprocessor, right? Okay, so hope you can see this. Mhm. um, in the previous semester, you have learned, especially especially in chapter 6, right, where you design actually the custom processor. So for example, you want to do one operation, right? Uh, so it takes, to complete one operation, it may takes, so you do the scheduling, right? So you have S1, S2, S3, S4, then you finish the operation. All right. So this is one operation. So in this case, how many cycles you take to finish one operation? So you have one cycle, two cycle, three cycle, four cycle. So four cycles to takes to complete one operation. And this four cycle is normally in the clock cycle. Okay. So in this case, CISC normally takes more clock cycle to complete one instruction. That is meant by this CISC take more to complete one operation or one instruction. But RISC normally will take less cycle to complete one operation. Right. That is the meaning of this. Number 2. Number 3, number of clock cycle to execute each instruction can vary. In other words, complex and variable length instruction. Most of the instruction takes the same number of clock cycle to execute. Simple standardized instruction. So this is related to this also, yeah, where again this is 4 clock cycle, right? So if we draw the clock like this, if it takes 4 clock cycle to complete one instruction, right? So for CISC, the number of cycle to complete one instruction for different instruction can vary, can be different. Means that operation number 1 or instruction 1, you take maybe 4 cycle. Another instruction, for example, instruction number 2, you need 5 or more. This is instruction number 2. Let's name it instruction number 1. This is instruction 2. So it can be more than, or not fixed. It can be it can has many clock cycles, all right, for different instruction. Instruction A may take 4 clock cycle, instruction B may take 6, or maybe may take 8 or more. It's different, all right, for different instruction. That is for CISC. But for RISC, if this is instruction number 1, instruction 2, different instruction, instruction 2 has the same number of cycle, 4 cycle also, instruction 2. Instruction 3 also 4 cycle. So the number of instruction cycle for each instruction normally fixed for the RISC, or reduced instruction set computer. That is the meaning of this number of clock cycle for each instruction. Means that CISC is actually, in terms of complexity, the hardware is more complex as compared to the RISC. RISC, the hardware is less complex. Why? Give you this example. So let's, for example, we have a simple microprocessor system. So microprocessor comprises of the processing unit. So the brain is the ALU. So we can have the ALU. So you can draw ALU here. So this is how the ALU looks like. And you will need to have the internal register. So you have set of internal register. So register, I will not draw like what we have learned in the design, where we draw one register to like this individual register. No, now I will draw the register in the form of sets of register, means that many register. So we have, like, for example, this is register R0, this is register R1, this is register R2, and then maybe we have up to Rn register, right? Depend on the architecture. So of course we have the input from to the ALU is using the bus, the data bus, like this. All right. So let's say, for example, this is 8-bit, and we have the output from the ALU. We'll go back to the register. So this arrow means that can go to any of the register. Yeah, can be R1, Rn, R2, R1, R0. This also, right? So this is a simplified drawing. Okay. And also, and of course we have multiplexer here, but I just ignore that. And also we have the memory. So the memory is outside of the microprocessor. It is actually outside the microprocessor. The RAM, yeah, it's outside. But to be a complete microprocessor system, you need to have a memory, and also the that is the core of the microprocessor, where you have the ALU and register, and also the control circuit. But I not include the control circuit in this. Yeah, make it simple. So you will have the memory, and the memory is quite big, right? So the register is actually the memory as well, but it is inside, yeah, or we call it internal memory, but this is external memory. For example, RAM. So you can have the address from address 0 to address maybe 1K in size. So in hexadecimal we use, this is FFF, right? This is location number 0, location number 1, number 2, until you have FFF. So it will be yeah, connected to here also, and this is connected to the same bus also, right? Looks like that. So for RISC architecture, for example, if we want to do add operation. For example, we want to add the content of memory, uh, memory location 0 plus 2. We want to do this in RISC, yeah. We want to do this. We want to add the content of memory location 0 plus the content of memory location 1, and the result is stored in memory location 3 or 2, right? Means that if you have number here, number 1, number 2, so we want to add number 1, number 2, and save the result in this location. So the result must be 3, right? If we perform this operation, that is the concept, right? But how the microprocessor do perform this job or task? So in RISC microprocessor, RISC microprocessor, what we need to do is we need to get the data from location number 0, put into the internal register, whether you want to use R0, R1, R2, depend on you. And also take this, put in our internal register, and then add using the LU and save it back to the internal register. After that, you send it back to memory location number 2. That is how. So in our RISC architecture, what you need to do is you need to, for example, you transfer the data from memory location 0 to R0 using one instruction. This represents one instruction. One instruction. And then what you need to do next is you move or get or read, yeah, this value into R1 using another instruction, right? Similar to this instruction, but the destination and the similar to this instruction, but the location is different. So we have the data in R1 and R0 and R1 already. Then we can add using the LU, using add operation, right? Then we can save in R2, for example. So what we do is R0 plus R1. Then we get the result in R2. Then we need to save it back to memory location number 2, right? From R2. So then you get the result equal to 3 in this. Right? So that is RISC. So you need at least the 4 instruction, 4 code in order to do that. Right? And for example, if one code, yeah, the CS control, the control vector is 8-bit to do this operation, 8-bit. So this one is also 8-bit. Normally it is the same size. This one is 8-bit also. This one is 8-bit also. So the control unit will produce the control unit that you create is will produce the control signal, the 8-bit control signal, right? Right? That is for RISC. But for CISC, the instruction is very comprehensive, very robust, that you only need one instruction to do the same operation. So you can have the instruction like this in CISC, where you can have memory number 3 plus, uh, this is wrong, right? We have memory number 2 is should be memory number 0 plus memory number 1. Only one instruction. Only one instruction, you can do that already. Compared to the RISC, you need to use 4 instruction. But this one, you use one instruction. But this is actually in terms of the architecture here, it is still the same. So what is the difference between this and this? So the difference is that the control design, right? So for example, this one, you have the similar operation, and this is 8-bit. But this one, CIC, you can actually you can do the move everything here. You can do, you also can do, and you can do this also, means that the controller or control unit must be more complicated, more bigger as compared to the CISC, because CISC don't have the ability to do this. Don't have. If you want to add number in the memory, you need to use the instruction that move the data to the internal register, add and move it back to the memory. All right. So in terms of controller, you have the very basic controller, right? But for CISC, you can do this, and also you can do this, and many more actually, many more. So in terms of control unit, controller, control circuit, it is a lot more bigger. So to do this, maybe your control sequence need to have 12-bit, right? You have 8-bit here, you have 12-bit here, and other operation maybe many bits, many other bits, right? So in terms of architecture, because of that, this one is CIC is a lot more complicated as compared to RISC, right? That is the meaning of this, right? Hardware centric, because hardware is complicated as compared to this. This is called software centric. Why? Because when we look back at this, yeah, in terms of software complexity, this is more complex, because to do the same operation, you need to have 4 instructions. This one, you have only one instruction. So in terms of software complexity, this one is more complicated, all right, as compared to this one. That is the meaning of this software centric. Less hardware complexity, of course. I have explained this. Yeah. Next is large number of instruction. So CISC you will have, yeah, because again, if you look at this example, you have this in all of this instruction and you have additional instruction like this. Of course, the number of instruction is very, very big later on, right? So that is why we have large number of instruction here, and here we have small number of instruction, right? And the last one is the compound addressing mode. We will see what is addressing mode in chapter 2, right? Addressing mode is the method, yeah, the way of how the microprocessor get the data from the memory and also from the register, right? So in short, CISC has more addressing mode as compared to RISC architecture, right? Because of this also, you can see that we have a lot of instruction for CISC, and of course, addressing mode also uh, larger, bigger as compared to RISC, right? So that is the difference between the two. So you will maybe now you cannot get the idea about this yet, but later on when you learn the architecture in chapter 2, you will start to realize the differences between the two, right? Okay, so this is the same thing that I have explained. Yeah, same things. So uh, we are almost 4:30, and hold on. About half of chapter 1. So I think we cannot complete chapter 1 by today, but good progress. The rest is will be the microprocessor system. What is the microprocessor system, and what is the difference between the microprocessor and microcontroller? And we will look at the ARM processor core, the one that we will use in this course, right? The ARM processor core, and the rest after this will be the ARM uh, processor core. And this ARM processor core, ARM is actually from advanced RISC machine. Yeah, ARM is advanced RISC machine, right? So if you search on the internet, this is the very famous, very popular architecture that is used in many processor today. Yeah, so this is some of the list that use ARM architecture. So we have many: Atmel, NXP, Fujitsu, Sharp, Texas Instrument, Qualcomm is the one that is inside most of the mobile phones that we have today. Even the Apple A microprocessor is based on ARM processor core. So you are lucky that we will be we will learn this architecture, this technology, right? So we will see this. Maybe I try to finish this by maybe take about half an hour for next week, but not today. I think 4:30. And by the way, any question? Any question that you want to know regarding microprocessor? Oh,
No, doctor,
no,
all good, doctor.
no aja eh. Okay, So if no, right. So if no question, so we will end our session now here. Thank you and see you next week. So I will share. Oh, one more thing. The software that we will use. I will share the link to download in Telegram lah. Yeah. Okay. Thank you. See you next week.